Students, physics class 12, electric potential. This is video number 2. In video number 1, you read that what is electric potential and the formula related to electric potential. Some other formula related to electric potential is related to electric dipole is electric dipole. You know that electric dipole. Electric dipole. What is electric dipole? When two equal magnitude and opposite sign charge are placed very small distance to each other, and they form electric dipole. And now we read about the electric potential due to electric dipole. For this, there are two positions are given: end-on position and broadside-on position. So first we read about end-on position. End-on position on the axis of the dipole. Suppose this is any electric dipole which is made of minus q and plus q charge. Suppose AB is the electric dipole, which is made of minus q and plus q charge, and distance between them is 2L. It is placed in a medium whose dielectric constant is K, and C is any point at a distance R. Okay? From middle point O of the dipole, at which we have to find out the electric potential. So first we know the formula, the electric potential at any point due to point charge. First we find out the potential at this point due to this charge. V1 is equal to 1 upon 4 pi epsilon naught K Q upon this distance is R minus L. The O is middle point, that is why R minus L. Now the electric potential at point C due to plus Q charge. This is plus Q charge and this is minus Q charge. V2 is equal to 1 upon 4 pi epsilon naught K Q upon R plus L. But since this is negative charge, that is why we have to take sign of charge minus Q upon R plus L. That is V1 and V2. So net electric potential at point C, V is equal to V1 plus V2. V1 is 1 upon 4 pi epsilon naught K Q upon R minus L, 1 upon 4 pi epsilon naught K Q upon R plus L. So V is equal to 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught. Now solve it. Q as a common, 1 upon R minus L, minus 1 upon R plus L. V is equal to 1 upon 4 pi epsilon naught K Q, taking R square minus L square as LCM, multiply that. This is R minus L minus R plus L. R cancel out. R plus L minus R plus L. V is equal to 1 upon 4 pi epsilon naught K Q into 2L upon R square minus L square. Q into 2L is P. If the electric dipole moment is P is equal to Q into 2L. So V is equal to 1 upon 4 pi epsilon naught K P upon R square minus L square. Since the value of R is very greater than 12, the value of R is very greater than 12, L tending to 0. That is why V is equal to 1 upon 4 pi epsilon naught K P upon R square. Now this is the formula of electric potential. And for air or vacuum, you know that the value of K is 1. That is why the electric potential 1 upon 4 pi epsilon naught P upon R square. This is the formula. This is the formula of electric potential at any point on the axis of the dipole. On the axis of the dipole, due to the electric dipole, is electric dipole moment R square. The electric potential at any point due to electric dipole is inversely proportional to R square, and intensity of electric field is inversely proportional to R cube. You read that before chapter. Now, end-on position. Next is broadside-on position. When the point is taken just perpendicular to the electric dipole, when the point is taken on the axis of the dipole, that is called end-on position. When the point is taken on the perpendicular of the dipole, that is called broadside-on position. Or on the equatorial line, broadside on position. Broadside on position. Suppose ABB is the electric dipole, which is made of minus q and plus q charge, and the distance between is 2L. It is placed in a medium whose dielectric constant is K. Now, seize any point at a distance R from middle point of the O of the dipole. Seize any point. We have to find out the electric potential at this point. This is perpendicular. That is called Gauss-Seidel position. First, we find out the electric potential at point C due to plus q charge. So we have to take this distance, and this distance is under root R square plus L square by the Pythagoras theorem. And due to minus q charge, we have to take this distance. This is also under root R square plus L square. Okay. So due to plus q charge, the potential at point C, V1 due to plus q charge, V1 is equal to 1 upon 4 pi epsilon naught q upon under root R square plus L square. And due to minus q charge, the electric potential V2 is equal to 1 upon 4 pi epsilon naught q upon under root R square plus L square, but negative sign due to minus q charge. Resultant potential at point C due to electric dipole is V is equal to V1 plus V2 or 1 upon 4 pi epsilon naught q upon under root R square plus L square and 1 upon 4 pi epsilon naught q upon R square, again R square plus L square. V is equal to 0. The electric potential on Gauss-Seidel position is 0. But intensity of electric field is not 0. That are very important. Okay. This is Gauss-Seidel position. Now, next heading is the work done on rotating dipole in an electric field. If we rotate any electric dipole in an external electric field, the formula of work done is work done on rotating electric dipole in an uniform electric field. Work done on rotating electric dipole in electric field. Okay, so work done on rotating. We know that when any electric dipole is placed in an external electric field, the torque acts on it, tau is equal to P sin theta. You know that. When we rotate, it's at this small angle d theta. Then small work done dw is equal to tau into d theta. So dw is equal to tau. The value of tau is P sin theta d theta. This is small work done. And total work done on rotating it from 0 to angle theta, W is equal to from 0 to theta E sin theta d theta. W is equal to E, the value of sin theta is integration of 0 to theta sin theta d theta. W is equal to P integration sin theta is minus cos theta from 0 to theta limit. This is the formula of work done on rotating any body, which you read in rotating motion class first year. dw is equal to tau into theta. When we displace any body, the work done is W is equal to F into dx, force into displacement. When anybody rotates, the work done is equal to torque into angular displacement. Now 0 to theta, the W is equal to P minus, as a common, when upper limit cos theta minus cos 0. The value of cos 0 is 1 minus P cos theta minus 1. Multiplying P 1 minus cos theta. This is the formula of work done on rotating the dipole in an uniform electric field. If it is rotated angle 90, theta 90, then work done W is equal to P. If it is rotated at angle 180, then work done cos 180 is minus 1 is plus 1, the work is 2P. 2P E. That is the one. This is the formula, the work done on rotating electric dipole. Now last heading is of this chapter is electric potential energy. Electric potential energy of electric dipole in an electric field. Electric potential energy of electric dipole in electric field. Okay. Suppose this is uniform electric field in which any electric dipole is taken from infinity. Any dipole, electric dipole which is made of minus q and plus q charge, and distance between them is 2l, AB. It is taken from infinity to the electric field. So as well as plus q charge is taken in the electric field, the force act on it in the direction of the electric field. And when negative charge enter in the electric field, the force act on it in the direction of the electric field. So we have to do work on positive charge, because the positive charge act force in the direction of the opposite. We are taken this type. We are taken toward the electric field, and negative charge experience force in the opposite direction of the electric field. So the work is obtained on minus q charge. But you know that minus q charge cover more distance to L to plus q charge. That is why the work done by taking plus q charge from infinity to this point is positive, and the work done of negative charge, work obtained from negative charge from infinity to point B is negative. That is why they are cancelled. And minus q charge cover more distance to L. So the net work obtained by taking this charge from infinity to the electric field minus F into 2L. And W is equal to F, the value of F is equal to QE into 2L. And Q into 2L is a electric dipole moment, Q into 2L. So W is equal to minus QE, minus PE. That is the work done by taking this charge from infinity to the electric field. And when it is rotated at an angle theta, the work done, W is equal to P bracket 1 minus cos theta. Now total work done, W is equal to, by taking this charge in the electric field and rotating it, W is equal to W plus W dash. So W is equal to minus ka P or plus ka P minus ka P cos theta. That cancel. W is equal to minus P cos theta. Minus ka P cos theta. So this is the work done, and this is the potential energy of electric dipole, minus P cos theta. This is the potential energy of electric dipole in the electric field. Now this chapter is finished. Electric dipole. These are the formula related to electric dipole. Okay.